Today we're going to talk about related rates, and this is section 2.6 in the Larson Calculus book. And I've got some examples here that we're going to do, and then you'll have some homework problems to work on. So first of all, let's see what is a related rate problems. In the box here on the top of the page, in related rate problems, the goal is to calculate an unknown rate of change in terms of other rates of change that are known. The variables are related by an equation. The procedures are as follows. Number one, if possible, draw a diagram. That's not required, but sometimes it does help. And then we assign variables and restate the problem. We find an equation that relates the variables and differentiate, usually with respect to t, which is time. And then we use the given data to find the unknown derivative. Okay, so here we go. Example one. We have a 16-foot ladder leans against a wall. The bottom of the ladder is 5 feet from the wall at time t equals 0 and slides away from the wall at a rate of 3 feet per second. Find the velocity of the top of the ladder at time t equal 1. So I am going to start with a diagram. I have my wall, which is over here, that vertical wall, and then I have a ladder against it. And when I look at this ladder leaning against the wall, so here's the wall, the ladder is not going to change its length, so it is going to be a fixed value. So it's okay in this example to write what my fixed values are going to be. This is 16. Now everything else is going to be changing. The x value here is going to be changing, as well as this y value is going to be changing. So what do we know? It says that the ladder is 16 feet, which I've already got that on there. The bottom of the ladder is 5 feet from the wall at time t equals 0. Okay, so let's kind of put that on hold just for a minute. And then it slides away from the wall at a rate of 3 feet per second. Now the ladder is moving away from the wall, so the horizontal value is going to be what's changing. The bottom of the ladder is 5 feet from the wall, and at the bottom of the ladder is what's sliding away from the wall at a rate of 3 feet per second. So that means my rate of change of that x value, dx dt, is equal to 3 feet per second. Okay, we also knew that at time t equals 0, the ladder was 5 feet from the wall, so x would be equal to 5. It says find the velocity at the top of the ladder at time, find the velocity of the top of the ladder at time t equal 1. Okay, so what I'm trying to find, let me kind of write that in maybe a different color. What I'm trying to find is my dy dt at t equal to 1. And I have taken up all the space that I have right now. Let's see if I can write this down here. Find dy dt at t equal 1. Okay. So I look at my diagram and I'm realizing this is a right triangle. So the only formula that I can come up with is my Pythagorean theorem. So your original diagram, my x is changing, so I have x squared. My y will be changing, so that has to be a variable plus y squared. That's equal to my hypotenuse squared. So there's my Pythagorean theorem. Now I'm needing to find my dy dt, so I'm going to find the derivative of each one of these variables with respect to t. Now remember your implicit differentiation. Since I'm finding the derivative of 2x with respect to t, that would be 2x dx dt, and my y squared, the derivative of that would be 2y dy dt, and the derivative of 16 squared is just 0. Now, to make things easier for myself, I'm going to divide everything by 2. So I have x dx dt plus y dy dt equal to 0. Now, I need to find out the velocity when my time is equal to 1. Now, if you notice this, all I have is x's and y's. So I need to find out one more piece of information. When t is equal to 1, I'm going to need to know the x value and probably the y value as well, because I have an x and a y here that I'm going to have to substitute in for. When t is equal to 1, what is x going to be equal to? Now let you stop and think about that for a minute. And you have to remember that x is starting at 5 and it's moving 3 feet per second. If at t equals 0, x is equal to 5, in 1 second, won't it have moved 3 feet? So wouldn't x be equal to 8? So I have to know that information. I also see in my equation, let's see, I can substitute in a dx dt. I can substitute in now my value for x, which is 8. I now need to find y because I am trying to solve for dy dt, the velocity of the top of the ladder. So this is what I'm trying to solve for right here. So I need to get um, values for the rest of those variables. So y, how can we get y? Well, I know x is 8, and I have an original equation. I just don't know if I have enough space for that, but we'll try. Okay, so if at x equal to 8, I would have 64 plus y squared equal to 16 squared. Oops, running out of room off the side of the page. So I'd get y squared equal to 16 squared minus 64 is going to be 192. So y is going to be 8 radical 3. Okay, so now I've got all my information to plug in my values for x, y, and the xtt. So let's see if I can squeeze it in here. I don't know that I can. Okay, here we go. We'll try. I have x, what was x again? X is 8. The xdt is, oh, by the way, I forgot to mention, since x is increasing, it's moving to the right, this down here, this will be always increasing, so my xdt is a positive 3 feet per second. So if the x value is increasing, it'll be positive. If it's decreasing, that value will be negative. Okay, dx/dt we said was 3 plus my y, which is my 8 radical 3, and dy dt is equal to 0. Okay, so do your math magic. Move your 24 to the other side. It becomes negative, and then divide by the 8 radical 3. I get dy dt is equal to negative 24 over 8 radical 3. And again, you do not have to rationalize, but we do need to put in our units. And our units would be feet per second. And I don't have any room to put that in there. So there's my units. Let's insert that there. Now, whenever you do a related rate problem, I always go back and look at the question. It says, find the velocity. So you have to give me a little sentence here. And again, I have no room to write it, so I'm going to write it above where it says example 1. This is how you finish up your problem. The velocity of the top of the ladder is negative 24 over 8 radical 3 feet per second at t equal to 1. Okay, velocity of the top of the ladder is negative 24 over 8 radical 3 feet per second at t equal 1. And again, I've answered all the questions. I've answered the question that they were asking, and I also have to put in, this is very important, at what time is that happening? If you don't have at t equal to 1, you miss the problem because the velocity is not always the same in every problem. Okay. Now, the other thing I wanted to mention is another way you could respond to that question is you could say the height of the ladder is decreasing at a rate of 24 over 8 radical 3 feet per second when t is equal to 1. Notice on that one I did not put the negative with that because I said the ladder was decreasing at a rate. So I don't put decreasing and then put the negative with your actual velocity. You can't put both of those because then they'll count that wrong, or I'll count that wrong. Okay, so ask me about that in class, and we'll go over that again if you don't understand that second sentence that I mentioned. Example 2. Water pours into a fish tank at a rate of 3 cubic feet per minute. How fast is the water level rising if the base of the tank is a rectangle of dimensions 2 by 3? All right, so what I'd like for you to do, I would like you to maybe sketch a diagram, write down what you're trying to find, write down what you know, and come up with a formula. So if the sub could put me on pause and give everybody a couple minutes to do that, and then we could come back and see how you did. Okay, here we go. Here is my cube, I guess you could say, my fish tank, and my fish tank's going to have some water in it. So here's my water level. And the water level right here, let's see if I can put this in. There's my H. That's the height of the water. And I know that this is a 2 by 3. Didn't it say it was a rectangular base? Yep, 2 by 3 feet. Okay, what are we trying to find? Did you figure that out? We're trying to find how fast the water level is rising. So we're trying to find dH dt. What do you know? This is what I know. I know that the volume, let's see, water pours into a fish tank at a rate of 3 cubic feet per minute. So that would be my, okay, it's pouring into the fish tank. It's a cubic feet per minute units. So I'm going to know that that's going to be the derivative of my volume. And that's going to be, it's increasing, so it's positive 3 feet cubed per minute. And I need to come up with a formula. So if I'm looking at my formula, all I can think of is volume is length times width times height. 2 times 3 times h. Okay? It's an h. So my volume that I'm going to be working with is just 6h. So let's find the derivative. Oh, by the way, how did you do? Did I give you one that was too easy and you tried to put too many variables in there? Okay, so this is bothering me because this doesn't look like an H. All right, so my dV dt, the derivative of the volume with respect to time, is going to be 6 dH dt. So now let's plug in what we know. We're just trying to find dH dt. We know dV dt is 3 dH dt. So dH dt is just 1/2. Now, what would be my units? That would be feet per minute. Okay, so let's kind of erase this here and write it differently. So I'm going to say that my dH dt is equal to 1/2 feet per minute. Okay, now go back to the question. It says, how fast is the water level rising? So let's answer that question. The water is rising at a rate of 1/2 feet per minute. Okay, there it is. All right, let's do some, those are pretty basic, I'll be honest with you. We got to do some a little bit more complicated, and that's what the rest of the problems are all about. Okay, so here we go. Example 3. Water pours into a conical tank of height 10 feet and radius 4 feet at a rate of 10 cubic feet per minute. How fast is the water level rising when it is 5 feet high? Okay, first of all, I left with you a formula of a page of a bunch of formulas from geometry. And I'll be honest with you, a volume of a cone, you will probably never have to have that formula memorized because on the AP test or on my test, I'll give you those equations. The things you need to have memorized are just like volumes of cubes, areas of circles. I mean, just the basic geometry formulas. When we get into cubes or anything, cones or anything like that, you'll be given the formula. So the volume of a cone, I'll give you that. The volume is 1/3 pi r squared h. Okay. So I'm looking at this, and what are we going to be seeing? What kind of diagram? Well, my conical tank, whenever you do these, they're going to be actually cones that are kind of upside down. Okay, so I'm looking at a radius of 4. Here's my height coming in here, perpendicular to that radius. We know that height is 10, so the whole thing is 10. And I have water coming in here again, so let's draw some water. And I don't know how high that water is. Okay, so this one right there is going to be h, and the height of the whole cone is 10. So when I look at this, again, I am not looking at the whole cone. I'm just looking at the part here. This is what draws my attention, this part. Let's get rid of the whole cone because it's kind of distracting. Okay, this is a set radius, that's 4, that doesn't change. This is a set height, that's 10, that doesn't change. The height of the water and the radius of the water, that will be changing. So here's an R and here's an H. Okay, so let's kind of figure this out. We have a, how fast is the water level rising? When it's 5 feet high. So I'm trying to find dH dt when the h is equal to 5 feet. That's my height. Now, if I look in here, I know that my radius, let's see, water pours into the conical tank at a rate of 10 cubic feet per minute. So again, that's my, what do I know? My dV dt, it's increasing, so it's going to be a positive 10 cubic feet per minute. And here's the issue here. I'm trying to find dH dt. I know dV dt. I know h is 5. Do they ever reference my radius? Do they ever reference that anywhere? Do I need to find dr dt, or did they give me dr dt? And the answer to both of those is no. So I want to get rid of that variable r. So now we got to really think about geometry and look at that diagram that I drew of that triangle. What do you see there that you can set up that would help you get rid of r? Or maybe write r in terms of h. And hopefully you look at that and think, oh yeah, I know, ratios, similar triangles. So I have, see if you guys got this. It's terrible talking to myself. Nobody can answer my questions. Did you get 4 over 10 equal to r over h, or something similar to that? So if I want to get r by itself, r is going to be 2/5 h. So I'm going to go to this volume equation right here, and I'm going to say, okay, that's going to be my pi over 3. Instead of my radius squared, I'm going to have 2/5 h quantity squared times h. So now I have changed my volume equation so it's in one variable. So do your math magic there, and I would get 4 pi over 75 times h cubed. Okay, now we're ready to find the derivative. Okay, doing my derivative of this, I would have dV dt equal to my 4 pi over 75 times my 3h squared. Don't forget your dH dt. Now we can substitute in our known values. I know my dV dt is 10. I'm going to go down here. Then I have 4 pi over 75. 3h. What was h? H was, can't find it, 5, and I have to square it. So that's going to be times 25, and I need to find dH dt. So there we go. We just solve for that. And I get my dH dt to be 10 over 4 pi. Okay? And you can reduce that if you want to. So I would just say, from here, let's write this out. It wanted to know how fast is the water level rising when it's 5 feet high. I would say the water level is rising or increasing at a rate of 5 over 2 pi. I could reduce that or leave it 10 over 4 pi feet per minute when h is equal to 5. Okay? So there we go. I think we're okay with all that. Oh, I forgot to answer part B. As time passes, what happens to the rate at which the water level rises? Can you guess what's going to happen to that rate as, what would be that rate of my dH dt as the water level rises? Well, if you think about it, as the water level rises, the radius is getting larger, which means the dr dt is going to be getting bigger. So it's going to slow down. It's going to slow down since dr dt will be getting big. Will be getting bigger. Okay. All right. First page down. Looks like we have 2 more problems. Is that right? Okay. A spy tracks a rocket through a telescope to determine its velocity. The rocket is traveling vertically from a launching pad located 10 kilometers away. At a certain moment, the spy's instruments show that the angle between the telescope and the ground is equal to pi over 3. Isn't that convenient? And it's changing at a rate of 0.5 radians per minute. What is a rocket's velocity at that moment? Okay, so I'm thinking about, I have a spy tracks a rocket through a telescope. Okay, so we're going to, and we have an angle between the ground. The telescope is right on the ground. Boy, there's no height to that telescope. I'm thinking about a right triangle here again. Okay, here's my theta value. I also know how far away is the spy from the rocket launch. The rocket is going vertically. That's why I knew I could do this right triangle. This is 10 kilometers. This height is going to be constantly changing, so I'm going to call that x. And I also know that d theta dt is, that angle is changing at a rate of 0.5 radians per minute. What do I need to find? I need to find the rocket's velocity at that moment. So the rocket's velocity, that's going to be my dx dt, because that rocket is going vertically, when theta is equal to pi over 3. Okay, that's what I need to find. My moment in time, I call that, my moment in time is pi over 3. Now, looking at this triangle, since I'm dealing with angles, I'm going to think more of like trig functions, sine, cosine, tangent. And I'm looking at this one, and I'm in favor of tangent of theta is equal to my x over 10. So get x by itself, and that would be 10 tangent theta. Can I find the derivative of this? Well, certainly. So I'm going to take the derivative of the tangent. I'm going to move this x to the left side. The derivative of x is dx dt. I always just like having that on the left side. And then on the right side, I'm going to take the derivative of my tan theta. So my 10 is going to tag along. The derivative of tangent is my secant squared theta. Now we have to take the derivative of theta with respect to time. Is going to be d theta dt. Okay, so I'm going to substitute in my pi over 3. So that would be the secant of pi over 3, all that squared. D theta dt was my 0.5, and so you just have to throw it in your calculator. Okay? Secant of pi over 3, do you remember what that is? That's going to be a 2 squared. That will be a 4 times 1/2. So I get 20 kilometers. Is it kilometers? Yep, per minute. Okay, so it's answering the question here. What is a rocket's velocity at that moment? So we're going to write it out. See if I can squeeze it in here. The rocket's velocity, I can't write that in there. The rocket's velocity when theta is equal to pi over 3 is 20 kilometers per minute. There it is. Okay. So we have one more left. How would you like to try this one with your partner? You want to give it a try? Why don't you get to the point of getting everything set up, and then maybe you can turn everything back on and see if you have it set up correctly. Okay, so why don't you pause the video, and then you can set up example 5 and see, before you do all the calculus, just see if you've got it all set up. So take a couple minutes to work with your partner. Okay, let's see how you did. I set up my triangle this way, and I just wanted to show you something that I did on my little triangle is when they're giving me directions, sometimes I'll put in those little vector direction notation. It says that one train is going away or like north of Chicago. So I'm going to put from C to B, I'm going to show that arrow going up. So I know that that distance is getting larger, so that that side's derivative would be positive. I'm going to call that side y. I'm going to call my hypotenuse z. And the other train is moving west, so that means it's getting closer to Chicago. So that distance between C and A is getting smaller, so that derivative, I'm going to call that x, should be negative because that one's getting smaller. So let's figure out what you know. Okay, do you have dx dt, the one going towards Chicago? West is, we said that would be a negative, so I know my dx dt would be a negative 120 miles per hour. And then the other one, my dy dt, would be positive 90 miles per hour. Now the other thing they talk about, now the little triangle that I use right there, all those sides are going to be changing, so those have to be variables. They also talk about the first train is 10 miles east and the second train is 20 miles north when t is equal to 0. So that is something else that I know is when x is equal to 10, y is equal to 20. And this is at t equal to 0. Okay, now what you can do here is you can do another little triangle here and say, well, this is going to be 10. Which one's 10? X is 10. This is 20. You can find z at that moment in time just by using your Pythagorean theorem. So that would be my 10 radical 5 there. Okay, so that might be something that we need to know. So I do a separate triangle with that moment in time information. Okay, so looking at my first original triangle, I have my x, y, and z. I'm ready to write my equation. That would be x squared plus y squared equal to z squared. What are we trying to find? We're trying to find the rate at which the distance between the trains is changing. So I'm trying to find dz dt. Okay, I didn't write that down anywhere. I'm trying to find dz dt at, do I know a time? At t equals 0. Alrighty. Okay, so if you got it set up correctly, go ahead and finish it. Okay, I'll just go ahead and put my work up here so you can check it here in a minute. You can pause the video if you need to. Okay, if you can look here, what I did is I went ahead and did my derivatives. I did my 2x dx dt plus 2y dy dt and 2 is equal to 2z dz dt. Now to make things easier, I divided everything out by 2. And now I'm ready to substitute in for x. I have 10. For dx dt, I have negative 120. For y, I have 20. dy dt is 90. Z, oh, here we go. That's where that z comes in handy. If you found out right now that you needed z as you're working through the problem, then you go back and say, oh, how can I find z? And then you use that moment in time at t equals 0. We know we have 10 and 20 miles for the two values of those legs of the right triangle. So I would use my 10 radical 5, and then I'm trying to find dz dt. Okay, so then you can do all your simplification, and I got my dz dt to be equal to 600 over 10 radical 5, which I would reduce to 60 over radical 5. Now, I know we don't talk about miles per hour in that type of notation. Okay, I would take that as an acceptable answer. You can change it to 12 radical 5, but you usually don't talk about that either. So it's really 26.833 miles per hour. Okay. Now, I have still not answered my question. So what was the question? Calculate the rate at which the distance between the train is changing. So here we go, writing it all out. I would say the distance between the trains is increasing at a rate of 12 radical 5 miles per hour when t is equal to 0. Okay, so part B, 10 minutes later, we still need to find that dz dt. So 10 minutes later, now we have to be very careful. My time was in, my rates earlier were in miles per hour. So now they're trying to trick us and give us minutes. So we can very easily see past that trickery. And we know that that's just 1/6 of an hour. Okay. So how much further has everything traveled? Okay, so let's think about this. In the x direction, I'm going 120 miles per hour. So if I do 120 divided by 6 in 10 minutes, I've gone 20 miles further in the x direction. Okay? If I take my 90 divided by 6, that's 15 miles further in the y direction. Okay? So if I think about this, let's set up my little triangle. Here's Chicago. Here was going north. And if I have gone, okay, so I'm thinking about this. I knew at time t equals 0, the train in the x direction was 10 miles east. So it has gone to the left 20 miles. So you got to think about this. Coming this direction, it's gone the 10 miles plus 10 more miles. It's gone past Chicago. Whoops. Okay, but remember we started over here at 10 when t equals 0. X was equal to 10. Was that right? Do I have that right? Yep. Okay, so we have the y direction going this way. We started at a y value of 20, and I've gone 15 miles further, so this is 35, and I've got this hypotenuse that I now need to find. So I can think about that. 35 squared plus 10 squared, I get 1325. Okay. And I take the square root of that. So now my rate at which my x is traveling is now a positive value. So when I go to substitute in my x dx dt, I'm plugging it into this equation, plus y dy dt equal to z dz dt. Well, now I have x is now 10. My x is now increasing, so it's now a positive 120. My y is 35. dy dt is still positive, but now my z is the square root of 1325 dz dt. There it is. Okay, so I can solve for dz dt, and I got a final answer of 4350 all over the square root of 1325. That would be miles per hour, which is approximately 119.504 miles per hour. Okay, so if I were to write this all out, I would say the distance between the trains is increasing at a rate of 12, oh no, gotta get the right number. That gave the wrong one. At a rate of 4350 over square root of 1325 miles per hour when t equal 1/6 of an hour. Okay? And I think that is it. So if you can spend your time now working on your homework, that would be great. And you guys have a great day.